In the last lecture, we proved finiteness of class group of a number field. To prove that, we used height of an algebraic number, and this naive notion of height was good enough to give us the theoretical result that ideal class group is finite. But the proof, although you can turn it into an algorithm to compute the ideal class group, it's a very impractical algorithm. So, let me just demonstrate the bounds that it gives in case of simplest of number fields. So, here is an example of the number field q square root of minus 5. This is just a quadratic extension of q, and we saw that 1 and square root of minus 5 is an integral basis of this. So, one of the quantities that appears in the proof is c, which is max of height of alpha I alpha j. So, this turns out to be height of 1, height of square root of minus 5, height of 5, which is clearly equal to 5, and then the other quantity that appears, which is in terms of c, is n times c plus 1 to the n plus 1, which in this case turns out to be 145, and we have to consider all ideals with norm less than equal to 145 factorial, and this is such a huge number even for this quadratic field with a relatively small discriminant. So, this proof is completely impractical to do any numerical computations, and so we are going to look at a second proof today, where we use norms of ideals instead of heights of algebraic numbers, and this will give a more practical way of computing ideal class group, and later in the course we will also look at examples on how to do this. Okay, so the basic question that we want to ask is in geometry of numbers is the following. So, question, let lambda in R to the n be a lattice, okay, and so it is not surprising that we are considering lattices. Rings of integers is a lattice in R to the n, as we proved earlier in the course, and then we want to consider a subset of R to the n. So, let S be a subset of R to the n, and in the proof this subset will typically appear as all elements of R to the n with bounded norm. So, norm in the sense of distance from the origin, okay. And so, we want to know when is S intersected with lambda non-empty. So, here is this very vague question in some sense, because I have not put any condition on my subset S and any condition on lambda apart from the fact that it is a lattice. So, of course, if you take S to be complement of lambda, you will never have anything like this, and even if S has nice properties, for example, it is contractible, it is like a disk, you may not have this, because it could be long in one direction where it misses all the points of lambda. But fortunately, this question has a nice answer by putting some properties on the set S, and so that is what I am going to tell you next. So, here is a definition, everything elementary that I am sure you have seen before. So, let S be a subset of R to the n, then S is said to be bounded. So, firstly bounded if there exists C greater than 0 such that mod of x is less than c for all x in S. So, this is the notion of boundedness in the usual way of analysis, first course in analysis that you learn. Then S is closed, I will not define that. S is convex if for any 2 points x and y in S, t times x plus 1 minus t times y is in S for all t between 0 and 1. So, the line segment that joins x and y is completely inside S, and the last condition we want on S is symmetric about origin. So, symmetric about origin if if x belongs to S implies that minus x is also in S. Okay. All right. So, the main result about geometry of numbers that we are going to use is the following. So, let lambda be a lattice in R to the n. Okay. Let S be a bounded closed convex subset of R to the n, symmetric about origin, then S intersected not just. So, we are I am saying that x is symmetric about origin. So, if S is symmetric about origin. So, if S contains a point x, then it will contain point minus x, and hence it will contain point 0, because 0 is half of x plus half of minus x, for example. So, 0 will always be, the origin will always be in the set S as long as S is non-empty. So, we want to say something interesting, that is why we remove the origin from lambda, and we are saying that S intersected with lambda. So, S contains a non-zero point in the lattice if volume of S is large enough. Okay. So, you can of course okay. So, you can of course imagine that S has all these properties of being closed, bounded, etc., without actually containing any point of lambda. But so you need to have some lower bound on the volume. So, let me read this statement got erased. So, let me rewrite the statement again. Closed, bounded, convex subset of R to the n, symmetric about the origin, then S intersected with lambda minus 0 is non-empty if volume of S is large enough. So, volume of S is bigger than or equal to 2 to the power n, this n being same as the dimension of R to the n, volume of R to the n mod lambda. So, R to the n mod lambda is some sort of n dimensional parallelepiped, and it has a volume, and you want volume of S to be bigger than or equal to 2 to the n times this volume. Okay. So, this is one of the main results that we are going to use at least twice in this course. So, here is a proof of this. So, what we are going to do first is we are going to prove this result in the case when so first assume that volume of S is strictly bigger than 2 to the n times volume of R to the n mod lambda. So, we are going to assume we are going to have a stronger hypothesis that volume is strictly bigger than what we want, and for this, when we do this, we do not need to assume that S is closed, and eventually we are going to make the dilate S smaller and smaller, so that we will use closeness of S. Okay. So, here is the idea is pretty simple. What you do is you consider the map from half of S to R to the n mod lambda. Okay. So, so what is half of S? Half of S, this is all 1 by 2 x such that x is in S. Okay. So, for every element x in S, so it consists of n coordinates, you take half of all of those coordinates. Okay. So, you can think of shrinking the set S in by half from every direction. Okay. Okay. Anyway, and what is this map? Let me try to tell you what this map is. So, half of S is contained in R to the n. There is a natural inclusion map like this, and from R to the n there is a natural surjection R to the n mod lambda, and what I want is the composition of the two. So, this is this map half of S going to R to the n mod lambda. Okay. So, there is a natural map like this, it just is induced by inclusion of half of S in R to the n. Okay. Now, if this map is 1 to 1, what do we know? Well, if this map is 1 to 1, then volume of half of S will be strictly well, not strictly, but less than or equal to volume of R to the n mod lambda. Okay. And what happens when you half the volume, half the set, okay, from every direction? For example, think of a square which is in 2 dimension. So, if you half each side of the square, you get a square of half the side, and its volume is which in 2 dimensional case is area, decreases by 4. Similarly, if you have a cube which is a 3 dimensional body, if you take a smaller cube of half the side, its volume decreases by 8, and so in this case what you have is this is 1 by 2 to the n volume of S. Okay. So, then volume of S is less than or equal to 2 to the power n volume of R to the n by lambda. Okay. So, you see where 2 to the n comes from. So, this is a contradiction. So, we want that is why we are using this stronger hypothesis that volume of S is strictly bigger than 2 to the n volume of R to the n by 2. Okay. Now, so this means so therefore, half S to R to the n mod lambda is not 1 to 1. Okay. So, that is what we have concluded. So, there are points P1 and P2 in half S, P1 not equal to P2, whose image in R to the n mod lambda is the same, okay, which means that P1 minus P2 is actually in lambda. Okay. So, this is what it means. Now, as P2 is in half S, 2 times P2 is in S and minus 2 times P2 is also in S. So, this is where we are using symmetry about the origin, and 2 times P1 is also in S because P1 is in half of S, and so we get half of P1 2 times P1 okay. I think I will just continue from where we left. So we are first assuming that volume of S is strictly bigger than 2 to the n times volume of R to the n mod lambda, and we concluded that this map is not 1 to 1. Okay. So, there exists P1 and P2 in half of S such that P1 minus P2 is in lambda. Therefore, we have half times 2 P1 plus half times minus 2 P2 is in S intersected with lambda minus 0. Okay. So, this actually is not 0 because P1 is not equal to P2. So, this proves the lemma in this case. Okay. Next, we want to prove the lemma in the case of when we assume that volume of S is exactly equal to 2 to the, right, that is the only case remaining. So, next we assume that volume of S is exactly equal to 2 to the n times volume of R to the n by lambda. Okay. So, the idea in this case again is simple. What you do is you replace S by another set, this time not shrinking it, but slightly increasing it. So, take epsilon bigger than 0 and consider the set 1 plus epsilon times S. Okay. Now, volume of 1 plus epsilon times S is equal to 1 plus epsilon times 1 plus epsilon to the n times volume of S, which is strictly bigger than 2 to the n times volume of R to the n by lambda. Okay. Moreover, 1 plus epsilon S is closed, let me write it like convex, closed, bounded and symmetric about origin. So, it has all the properties that S had, which means 1 plus epsilon S intersected with lambda minus 0, this set is non-empty, right, by what we have proven before in the first case. Okay. Not only this, what do we know? Well, if I call this set q epsilon, then q epsilon is bounded because it is contained in the bounded set, and discrete because it is contained in the discrete set lambda, right. And what is a bounded discrete set in R to the n? It's a finite set. Moreover, if epsilon 1 is less than epsilon 2, then 1 plus epsilon 1 s is contained in 1 plus epsilon 2 s. Hence, q epsilon 1 is contained in q epsilon 2. Okay. Therefore, intersection of epsilon 0 q epsilon, this is equal to s intersected of lambda minus 0 is non-empty as S is closed. Okay. So, the first equality here uses the fact that S is closed. So, this proves the lemma. Okay. All right. So, if you have a bounded closed convex subset which is symmetric about origin and has large enough volume, then we can show that it contains it contains a non-zero point in a lattice. Okay. All right. So, we want to use this to prove finiteness of class group. So, what I am going to do now is I am going to tell you how to do that. So, here is the theorem that we have proven before, but we are going to see a second proof of this. All right. So, let f be a number field then, and let me remind myself how I denote class group CLK, then CLF is finite. Okay. And again the idea is the same. We will take any ideal class and we will show that it contains an integral ideal of bounded norm. Okay. All right. So, we have seen a map of this nature before. So, what I do is I take a map from F into R to the n, where n now is degree of F over Q. Okay. And what is this map? It takes alpha to sigma 1 alpha and so on up to sigma r 1 alpha, and then a real part of sigma r 1 plus 1 alpha and so on up to real part of sigma r 1 plus r 2 alpha, and then imaginary part of sigma r 1 plus 1 alpha and so on up to imaginary part of sigma r 1 plus r 2 of alpha. Okay. All right. So, we know that image of OF is a lattice in R to the n. Now, to begin with, we take S to be any subset which is closed, which has all the properties of the previous lemma, and that might seem counterintuitive that we could start with any set like that. but we can, because we are not going to use S itself, we are going to dilate S, we are going to shrink or increase S depending on our ideal class. Okay. So, let S be any closed bounded convex subset of R to the n symmetric about the origin okay, and this is what we will start with. Now, we want to dilate S, as I said, right, and what we are going to use two quantities for this. So, first V, so put V to be volume of S, right. At the moment we are taking S to be anything. So, this volume could be really tiny or it could be really large, we do not know. And the second quantity is something that is related to norm. Okay. So, what this is max of all the quantity like this. So, x 1 up to x r 1. So, mod of this, right, and then x r 1 plus 1 x r 1 plus r 2 plus 1. So, squares of these. So, I am taking this very complicated looking product, but this complicated looking product is what computes the norm of any algebraic element. So, this is such that x 1 up to x r 1 plus r 2 times r 2, this is an element of S. Okay. So, I am taking maximum of this product and I am calling that quantity M, right. So, if M is if S is really tiny concentrated around the origin, then M will be very small. If S is very and V will be very small, but if S is very large, sort of spreading out away from the origin, then volume will also be large and M will also be large. Okay. All right. So, here is a claim that I am not going to prove today, perhaps I will give it as an exercise. So, let A be any fractional ideal non-zero, then volume of V mod A inverse, this is equal to 2 to the minus R 2, and I take the discriminant of F to the power half and norm of A inverse. Okay. So, it is clear that this is the volume when you take A to be the ring of integers, and the claim is easy to prove from the fact that norm of A is same as the number of elements in OF mod A if A is a integral ideal, and from that you can deduce this claim. Okay. So, I am going to be quick, not explain really what is the motivation behind all these definitions, but I take lambda to be this, and now you consider lambda s and you look at its volume. It is easy to see that volume of this is 2 to the n times C, where C is this quantity. Okay. All right. So, hence we can apply the previous lemma A inverse intersected with lambda s, this is contains a non-zero element. Okay. So, let us call it alpha. All right. So, what do we know about alpha? Well, if I take norm of alpha, because of the fact that it is contained in lambda s, I get that norm of alpha is less than or equal to lambda to the n times m. Okay. Furthermore, because so this is as alpha is contained in lambda s, but furthermore alpha times a is contained in OF. This is because alpha belongs to A inverse, right, and that is the reason why we are doing this. And so, if you take norm of alpha times A, this is equal to norm of alpha times norm of A, which is less than or equal to 2 to the power R1 plus R2 times m times V inverse times the discriminant of A to the half. Okay. And now this quantity is independent, this is independent of A. Okay. This quantity, remember, m depends only on S, which we choose without any reference to A. V is volume of S, again which is chosen without, and df is just the discriminant. So, this quantity is independent of f. Now, alpha A is an integral ideal in the same class as A. Hence, we have proved our result. Hence, we have proven that any ideal class contains an integral ideal bounded with norm bounded by some quantity that is independent of the class. So, V inverse, okay, all right, and so hence CLF is finite. Okay. So, the last part is same as the one with heights. Okay. So, so this gives us another proof of finiteness of class group. Now, in the next lecture we are going to take a good choice of set S, so that we have a good handle on this quantity. Okay. So, we want to understand this quantity and we want a good handle on this quantity. And so, we can make good choices of our set S that we start with to get a to get a nice bound. So, that will be the subject of next lecture. Thank you.